Good evening, all of you. This is Dr. Subramanya Rao, Professor, Sasi Institute of Technology and Engineering, Tadepalgudem. I am dealing Signals and Systems course. In the previous classes, we have seen the first part of the first crucial part of the Signals and Systems, that is, what is a signal, classification of signals, operations on signals, and what is a system, classification of systems. With related problems we have completed. The next crucial one is transformations, mathematical transformations. So after studying signals and systems, if you take a signal, how can we transform? The famous transformation that we have that you might have studied in the first year is Fourier transform. So basically it is a Fourier analysis. Now we are going to apply this Fourier analysis to our signals. That is the motto behind it. So our next in this contest, in the Fourier analysis, first let us start with Fourier series. Then after that Fourier transform. So coming to the Fourier series representation of a particular signal, this is the root map. So for clear understanding of Fourier analysis, first we should start with analogy between vectors and signals. With this we can easily understand how can we represent a signal in terms of one signal or n number of signals. So later we are going to represent the ending of analogy between vectors and signals will leads to the definition of Fourier series. So there we start Fourier series representation. Then there is a condition for existence of Fourier series. Let us discuss that, that is existence of Fourier series. Finally, there are two types of Fourier series. One is trigonometric Fourier series and exponential Fourier series. Let us discuss it elaborately along with some problems. Okay, this is the route map for learning Fourier series. Frankly saying, for students of second BTech engineering students, exam point of view, this analogy may not help much, but for clear understanding of the Fourier series, only that root comes from this analogy only. So that's why try to concentrate on this topic also for clear understanding, especially for GATE aspirants. Yeah. First, the motto behind dealing this topic is, let us take an example. If you go to a mobile shop, you want to purchase one good mobile based on your budget, based on the availability of your budget. When you step into the shop, mobile shop, ultimately the mobile you search, you expect more, but all these expectations should come for less cost. So always you try to get one model, that is iPhone. So whatever the phone that you purchase should be very much towards iPhone, but you may not be your fund may not be sufficient to purchase iPhone. So below that you want to purchase one mobile, but all the specifications of the mobile may be towards iPhone, isn't it? Suppose if you choose a Samsung mobile, if it is very good and very nearer to iPhone, you prefer purchase if it comes for less cost. That is called approximation. So first you need to, everybody has to understand approximation. Your goal is to buy a very good mobile, but it may not be iPhone. The another phone that comes for less cost you prefer. So you are going to approximate your desire with a standard one, nothing but iPhone. That's the motto. Towards that only we are going to see the mathematical background for it. That is called approximation. So first, to discuss this approximation, first we start with vectors. If you understand the analogy between two vectors, we can apply the same for two signals. Okay, so first let us see analogy between two vectors. We know vector, let us take two vectors v1 and v2. What is our goal here? We are going to approximate a vector v1 in terms of v2. In the mobile example, this is the mobile that you want to purchase, but you always try to compare with a standard one, that is v2. So you know vector is one which contains both magnitude and direction. So let us see, suppose it is a vector v1 and this is vector v2. Our goal is to approximate v1 in terms of v2. So actually there are several ways. What is the extension of it? From the ending point of v1, you can draw several lines onto v2 for approximation. But we need to choose the best approximation. Generally the approximation is denoted as v1 is nearly equal to c1 to v2. I will explain you clearly what is the meaning behind it. v1 is nearly equal to, it means we are going to represent v1 in terms of v2 while representing some component of v1 along v2. That component is called c12. That component is called c12 into v2. Magnitude of that component is c12. So c12 is magnitude of component of v1 along v2. So this is called approximation. That's why we are using approximation, means opposite to exact. It is not exact representation. So v1 is nearly equal to this much. It means nearly equal to means there may be an error. Suppose if we take an example, 6 is nearly equal to 5. That is nearly equal to 5. When it is exactly equal to 6, 6 equal to 5 plus 1. So if we add 1, or how did we get that 1? Difference between 6 and 5. Difference between 6 and 5. That is called error. If you add with that error, then it is exactly equal. So it is exact representation with equal to symbol. This is approximate representation, approximative representation. So ultimately we need to see the error between these two. Error means v1 and the representation. That is called error vector. So here what is error vector? Let us represent it VE. What is VE? VE equal to V1 minus C1 to V2. What is our goal in this approximation? The error should be as small as possible. It means if you choose a mobile in the mobile shop, from the specification point of view, all these specifications are very much nearer to iPhone. So the error between these two should be as small as possible. Then only you will be satisfied. So always we search for minimized error. Minimized error. Okay. So we need to choose here in this approximation, C12 is chosen such a way that error between these two should be small. C12 is chosen such a way that the error between these two VE should be as small as possible. Okay. Next. So error should be small. So the representations drawn with blue color are nothing but error between these two. So which is the best approximation here? Where the error is less. Here if we observe, where do we get less error? When we draw a perpendicular line from here to here. Then this one is C1 to V2. Now this is fulfilled. Therefore, vector v1 is nearly equal to c1 to v2. Here we have chosen for minimum error. Suppose if I take this line, error line is more. If you observe, if I take this line, in all these error may be more. If you draw a perpendicular line on this, then error may be minimum. We need to choose like this. Okay, this is called approximation of one vector along another vector. Here we need to highlight one more term, that is orthogonal vectors. Orthogonal vectors. What is meant by orthogonal vectors? When one vector v1 has no component along another vector, then those two vectors are called orthogonal vectors. It means v1 has no component along v2. When is it possible? See, if two vectors are like this, there is a shadow of v1 on this. But if the angle increased, if the two vectors are perpendicular, there is no shadow of v1 along v2. Then this is the situation of orthogonal vectors. It means when the two vectors are mutually perpendicular, then there is no component of v1 along v2. Don't get confused. Component means you can remember it as shadow. V1, there is no v1 shadow in this situation on v2. It means there is no component of v1 along v2. Okay, that is represented in a different way. So v1 along v2, the component of v1 along v2 is denoted as, already we have seen, that is c1 to v2. From the vector point of view, we are going to calculate it is as v1 dot product of v1 and v2 divided by second vector magnitude v2. See, this is the magnitude of second vector. Okay, so this is one formula to find out the component, dot product of the two vectors v1 and v2 divided by that magnitude of the second one with which we are approximating. Okay, if you solve it, v1 dot v2, if you solve it, then what is c12? C12 is nothing but send v2 that side. Therefore, dot product of v1 and v2 divided by square, send this v2 here, v2 square. This is the formula for magnitude of, what is C12? Already told you, magnitude of component of v1 along v2. That formula is v1 dot v2 divided by v2 square. Now coming back to the orthogonal, what did I say? When the two vectors are orthogonal, if one vector has no component along another vector, then what will happen? If one vector has no component along another vector, you know the dot product formula, magnitude of v1 into magnitude of v2 into cos theta. Cos theta, cos 90 degrees phase angle, cos 90, it is 0. Therefore, the dot product here is v1 dot v2 will be 0. Will be 0. If v1 dot v2 equal to 0, then c12 equal to 0. c12 equal to 0. So with this formula, we can tell the orthogonality definition. So in two ways we can say that. If the component of one vector along another vector c12 is 0, then we can say that the two vectors are orthogonal. Vice versa, if two vectors are orthogonal, then the component c12 will be 0. In either ways, we can remember. Okay, that is the analogy between two vectors. Next, we can implement the same for two signals. Next, let us see it for signals. Yeah, we can easily extend the same concept what we have discussed for vectors to signals. Let us take two signals, x1 of t and x2 of t. Keep it in mind the same example, the mobile example what I explained earlier. So now our goal is to approximate one signal x1 of t along another signal x2 of t. Then what is that representation? x1 of t is nearly equal to c12 into x2 of t. This is the representation of that approximation. We are trying to approximate the first signal x1 of t along another standard signal x2 of t. In this, what is c12? The magnitude of the component of in this approximation, isn't it? Already we have seen earlier the relation between two vectors. How did we represent? And finally we defined orthogonality. Here also we can say. Again, in this approximation, ultimately there may be an error. What is the error? Error is the difference between these two. Therefore, that error signal, let us consider it as xc of t, is nothing but original x1 of t minus approximative component x2 of t. Here again, what is our goal? We need to choose the component c12 such a way that the error should be as small as possible. Whenever you get the best lower error, that is the best approximation, isn't it? So for explaining this for best approximation, what is our goal? Our goal is to find out the formula for c12. In earlier, c12 equal to v1 dot v2 divided by v2. Very easily using vector formula we told like that. Here we need to solve it. So for solving it, the error should be as small as possible. So for that, how error changes with respect to c12, for that we need to find out average of that average value of that error. That is also called as mean value of error. But there is a problem if you take the mean value. What is the mean value? Difference between these two xc of t integral in a particular interval, integral t1 to t2 xc of t dt, mean value no. So within a particular time interval t1 to t2 no, t2 minus t1. Actually this is the mean value. But what happens if you take the mean value? In this error, if we have positive values and negative values, they may be cancelled out. We may get error. So to avoid that, in all mathematical relations related to signals, we prefer mean square value. So that's why instead of mean value, let us take mean square value of error. Mean square value of error. That is very easy to find out. Let us denote it as E. That is, in a particular interval t2 minus t1, integral in this range t1 to t2, square of the error signal xe square of t dt. Generally what is mean value? Error divided by duration. Area under that error divided by duration. But there is a problem. So that's why we go for mean square error. Square of the magnitude of the error divided by the duration t2 minus t1. Okay, so if you substitute here, so I want to skip some of the general mathematical steps here. Let me substitute x1 of t minus c12 into x2 of t square dt. Already I told you our goal is to minimize the mean square error. For what purpose? To find out the c12. Our goal is to have value for c12 such a way that E should be small. For that, differentiates d by d c12 of this error and equate it to 0. So the maximum variation of this mean square error, if it is equated to 0, we can find out a formula for c12. Okay, I leave 2 or 3 steps for your own preparation. Finally, if you do this derivation and equating it to 0, we get a formula for C12. You can easily compare the formula what we get, we can compare it with vectors. So C12 equal to integral T1 to T2 first signal x1 of t into x2 of t dt divided by square of the second signal T1 to T2 x2 square of t dt. This is the C12 component. You can easily compare it with vectors. Let me write it once again. C12 equal to V1 dot V2 divided by V2 square. Same structure, instead of vectors we have signals. So this is the formula for C12. Now we can extend the same to the orthogonality. When two signals are orthogonal, when one signal has no component along another signal. So we can extend the same for orthogonality. Orthogonal signals. When two signals are said to be orthogonal, if x1 of t has no component along x2 of t, has no component along x2 of t. If it has no component along x1 of t, then C12 equal to 0. So again, so C12 equal to 0. If C12 equal to 0, if you observe substitute C12 here, this will also be 0. Therefore, what the condition for orthogonality is? Integral T1 to T2 x1 of t into x2 of t dt should be 0. This is the orthogonality condition. So two signals are said to be orthogonal if the component C12 equal to 0, nothing but the area under the product of the two signals should be 0. Area means integration. Then the two signals are said to be orthogonal. That's the end of this topic. In the next class, let us do some problems based on this orthogonality of signals.